Yeah, so we're gonna be recording here before we start. The opening session here, the keynotes and the closing will be recorded live. And later we're gonna upload that to YouTube. And the sessions, on the other hand, will not be recorded live. We have already the pre-recorded videos of the presentations. The authors have submitted that to us, so we're gonna be including those later on a YouTube channel, and we're gonna be posting all those information later on the program page. So let's start with me. Welcome from General Chair. My name is Giovanni. I'm the General Chair for PAM 2022, and I would just like to welcome you today and provide you some statistics about the number of registrants we have here today, number of participants. And up to 11 a.m. today, when I actually run the stats and look at the database, we had 182 registrations, but we had quite a few more since then. So our goal actually with this conference and this registration, it was to make it accessible to anyone. So what we did for this, in this sense, was to make free registrations for everybody. Nobody had to pay anything. And also that makes our life easy as well, because you don't have to handle all the payments and paperwork. And the second thing to make it available is that our papers are publicly available during the conference period and up to 4 weeks after that. But you have the caveat, it's that you have to download via our program page. So you got to go there, and that we're going to redirect you to the Springer, our publisher website. And if you come from our website, they're going to know it's you, so you can download it there. All right. So if you remember when you registered, we had 3 questions in the forms, besides your affiliation and name, your time zone, and if you would attend, if it would not be online, if it would be in person, and if you'll be willing to pay for a conference. And I'm just going to give you, some feedback on this data here. And turn out that most of the people who register were at the moment at the GMT +1 time zone, UTC +1, as you can see here in this high bar. And I think a lot of them, at least for those in Europe, have moved to 2 since the summertime stopped over the weekend here in Europe. But you see folks in here this is probably East Coast in Canada, and here is probably West Coast here too. Folks in Asia here, this -3 is Brazil. So I think we try to accommodate people from all over the world. That's why we're starting the conference now in the middle of the afternoon here in Europe. So people in California could also attend their early morning, it's the morning, super early morning. And people from Asia can also attend. Another question you ask, it's like if people would attend if the conference would be in person, and the default answer for the form for the question was not sure. So I said most people here were not sure. We don't know if that's the reality or if that's just left that way. But roughly 50 people said they would attend, and roughly a little bit more said they wouldn't attend. So in this conference, we would actually at least manage to get those people who wouldn't attend or if we wouldn't be online or otherwise. And you got to remember that when we started planning this conference in here, it was very unclear how the pandemic situation would be by the moment. At least here in Europe, now in the Netherlands, we could have had this conference in person, but it doesn't mean that we could have all the people flying over here and their countries would accept them and quarantines. So it wasn't clear. So that's why we decided to go for a virtual conference. Another question we asked if people would attend if be paid online and paid, and for most people that would be a problem. Some said no. So again, we are covering people here that wouldn't be willing to pay, which is good. Extending the coverage, and majority was not sure, but there's a bias here because it was also the default answer in the form. And this conference is only happening because of all the people who work in this conference, and I really have to thank everyone of those people here today. I'm going to start with the TPC channel, Christel and Oliver. They did a great job with the papers, and they personally helped me a lot through this conference. They're helping organize, and Oliver had been the chair for PAM 2021, so I could really tap in on his experience on the hosting an online conference and the tools. But I also got to thank Marco, he's not online at the moment, I guess, because he's traveling. He is the web chair for the conference. He did a bunch of things for the website. If you check the website, it supports IPv6, then SEC, a bunch of secured features. It's really up to date. So thanks a lot, Marco, for that. And Moritz Miller for being the registration chair. He contacted mail, sent people emails, links, and a bunch of other stuff. So thanks a lot for doing that. Casper helped us a lot not with the videos. He was responsible for downloading all the videos, normalizing them, checking each single them. Elmer Lasdracher, was in our online experience chair. He helped me a lot in setting up Zoom and make sure I could close all the corners here. And also we had a bunch of volunteers, the play out volunteers. Those are folks that are going to be playing the videos during the technical sessions, so the session chairs can be free to pay attention to the questions in the Slack channel or in the Zoom. And we have Carlos, Ganan, Samane, Sven, Max, and Simone here going to help us in this process here. And Elmer as well is going to help this, and Moritz. And also we had to ask some legal advice on we're going to be collecting, we had to collect registration information. So our colleagues, Martin, April, and Karen help us with that in this process. So thank you very much. Without those people, the conference would not be possible. I also have to say thanks to the host institution. It's the institution that where I work. It's SIDN Labs. SIDN Labs is actually the research arm of SIDN. SIDN is the registry of the Netherlands CCTLD, the country code TLD. And we have prepared a welcome video to you folks. So I'm going to try to play this right now. I'm going to stop sharing the screen in just a second. Screen mode. And I'm going to play the video. And share again. Share the screen. And you folks, let me know if you don't hear the audio, if the quality is bad. Yeah.
Hi, welcome to PAM 2022. My name is Christian Hesselman. I'm the director of SIDN Labs. SIDN is the operator of the Dutch top-level domain on the internet, .nl. We manage 6.2 million .nl domain names through our DNS infrastructure, which is distributed across the world and handles 2.5 billion DNS queries a day. This means that we're a critical infrastructure for both the Netherlands as well as for the internet at large. As a result, network measurements are key to our operations, and we're very proud and honored to be able to host the PAM conference this year. Because network measurements are so important to us, we're also active in this space ourselves through our research team, SIDN Labs. For example, we carry out large-scale internet measurements through RIPE Atlas and our DNS analytics platform, Entrada. This enables us to gain new insights into the evolution of the internet and security incidents that occur. As a result, we can also develop new types of tools that we make available to our own operations teams as well as to operations teams elsewhere. And we accomplish this by making our software open source and publishing our papers.
One example where measurements are fundamental here in our research is DNS engineering. SIDN operates .nl, so we want our DNS servers to deliver fast responses and at the same time to be resilient to denial of service attacks. With the goal of better engineer anycast servers, we have been working since 2015 with colleagues at the University of Southern California, ISI, on multiple measurements studies. These studies have now culminated in a soon-to-be-published RFC 9199 by the Internet Engineering Task Force, where we describe considerations for large DNS and cast operators, something we are very happy and proud of.
Another field where measurements play an important role is in the fight against domain name abuse. We often rely on machine learning to detect patterns in measurement data. For example, we've developed software to detect fake web shops using data collected by our own crawler. And like with most projects at SIDN Labs, we not only made sure that our detector can run reliably in production, but that we also contribute back to the academic community. We take their feedback into account to further improve work in this space, for example, by publishing a paper at a conference like PAM.
So these were two examples of projects that we run at SIDN Labs. Let me close by wishing everyone a great conference with lots of inspiration and new insights and potentially new collaborations at PAM 2022.
All right, so let's go back to the slides. Share the screen. Sure. All right, so tools. At PAM here 2022, we're basically using two tools, as you might have received the links. We are using Zoom, and we are using Zoom in a meeting mode, meaning that anyone can, during the Q&A, raise your hand and then tell the questions into the mic in the authors or video, and you can have an interactive session with the authors of the paper. Just a caveat, you have to raise your hand and wait for the session chair to call your name so you can go to the mic. We also have Slack. We'd like to ask you to avoid using the Zoom chat, which is it's not really nice compared to Slack. And we have created one channel per session. You can check in the program, and you can, for example, here, this is the session routing 2, and we see the Slack channel here underlined here in this figure, so you can see here, and join the sessions that you're interested. And I recommend the authors of the papers also to monitor their respective channels and interact in there too. If you're having any issues, you can drop me a line. Here's my email address, or you can also report on the general Slack channel. And I think that's all I had to say. So I'm going to start sharing here and handing over to the TPC chairs.
All right, then I would like to welcome you also from the PC chairs. So my name is Oliver Hohlfeld from Brandenburg University of Technology, and together with Crystal Pelzer from the University of Strasbourg, we had the great honor and pleasure to compile this year's PAM program that you will be enjoying over the next 3 days. So what we're going to do real quick in this opening is to guide you a little bit through this PC process. So how did we actually compile the program, and what kind of approaches did we follow here? So the first thing is that PAM is constantly evolving. So we carried over and we continued to use a few additions that were introduced last year. So that was the introduction of the review task force, the RTF, and the self-nominations for PCs. So that was introduced to PAM last year. It just went great, so we decided to continue using these processes. What we did add, in addition to all of these news that were introduced last year, was this year we now feature both the option to submit short papers, which is the traditional 12-page Springer LNCS format that we're used to. And then we added the addition to also submit long papers, which are double the size. So this is something new that we added to PAM this year, that we now have long papers, and we will just see in a couple of seconds of how that went in terms of the submission numbers that we get for both the short papers and the long papers. So as it was used last year, we had a self-nomination for PC, meaning that we formed and we compiled the largest PC that PAM ever had. So we had 70 PC members, including 6 RTF members, out of 2 input sources. So as typical, the PC chairs, they create and compile their own invitation list. So we had Crystal's and Oliver's invitation list. And then in addition, we had an open Google form where people could self-nominate themselves to be serving on the PC of PAM this year. So the open call for PC application, it just went great. We got 89 really strong applications, which was kind of troubling our job as PC chairs, because in the end, we got to select them. So we applied a number of selection criteria here. And the selection criteria were that we wanted to achieve diversity over the topics, the regions, the institutions, and the seniority of the PC members. So we admitted people that were rather junior, but also people that were rather senior. And one thing that was actually surprising to us was there were a couple of very senior PC members that we initially didn't dare to put on our own invitation list, because we thought that, you know, there is no way they ever accept our invitation. And then they self-nominated themselves to serve on the PAM PC. So that was just like a major success, having this open call, and we just, you know, proposed to continue using that. What we did was once we had the PC put together was we did organize a town hall meeting. So there was a meeting right after the submissions were all in, where the PC could meet and discuss about the review process and what we expect, how to best go about reviewing papers and so on. And it was just to align the PC because we had a wide diversity over junior people, very senior people from different areas of our community and so on. So that did serve as kind of an alignment process, and the discussion that we had in the town hall meeting went great. So this was a great addition to PAM. What we did discuss here was like a little bit about the reviewing process. So reviewing 101, what is the process? What do we expect? But then like the most crucial point here was like we had an open discussion where people were sharing their experience. And I'm very happy that many of the senior members of our community were very active here in these discussions and sharing their opinions on how to improve the review process and what to look out for. One particular statement that we were like continuously making, both during the town hall meeting and the actual initial emails that we were sending to the PC, was in the end, we want to have a program that for PAM to actually make happen. This is the desire that every PC chair is having. And we simply set out this simple statement that we want to be looking for accepting all papers that are technically correct and could offer some value to our audience. So there is no acceptive room. It's a virtual conference. We can simply make room. This is not, this should not limit us from accepting papers. And I think like adding this statement and repeating this statement here that we want to basically look out for accepting every paper that is technically correct, it just went great. So there were a couple of discussions where PC members said that, yeah, that's, I was on the fence, but the PC chairs initially said all the technically correct papers should be accepted. So this paper is technically correct. So I guess we should propose the acceptance of this paper. So I think like making this statement early on in the review process did make a lot of sense and helped to actually make decisions. The other thing was like last year we had a review task force, and the goal of the review task force was to oversee the entire review process to ensure that the reviews are high quality, constructive, and have a positive tone. So with that, I would like to thank all the RTF members that were serving on the RTF, and all of them did like a terrific job in joining the discussions, steering the discussions, and making sure that we arrive at a high quality program that you will enjoy over the next 3 days. So I would like to thank Anya, Fabian, Anna, Matthew, Mirja, and Mark. And with that, I would like to hand over to Christelle to tell you about how the submissions went.
Hello, everyone. So we received 92 paper registrations for PAM this year. Initially, we desk rejected one paper because it was not double-blind, and PAM has been double-blind since a few years. And then after that, we selected 62 submissions. So this program is composed of the presentation of 62 papers, 32 short papers, and 30 long papers. We had 4 reviews per paper with a load per PC member of 3 to 4 papers to review. You can go to the next slide. So the conference is double-blind, as I said before, and we had 2 weeks of online discussions before making final decisions with lengthy discussions for some of the papers. We assigned shepherds to 18 papers. So the papers where there was clearly nothing to change or very minor changes were not assigned shepherds this year. And only the papers with more changes were assigned shepherds. And finally, we had 3 papers where both Oliver and I were conflicted. So they were handled by Mark Allman. So we thank him again for this. You can go to the next slide. So we selected 62 papers, and in the end, we selected the same number of short and long papers. So the number of submissions for long and short papers were almost equal. We had 2 more long papers than we had short papers, but we accepted the same number of long and short papers. So we can go to the next slide. Here are some statistics on the origin of the corresponding authors. So where is the affiliation located? So as you can see, we have a major number of authors coming from the US and China. This is what you can see in blue, and then in orange is the origin of accepted papers. Can move on to the next slide. So for the program, we paid attention to try to start at the hour. So as you can see, today we start at 2, and then the next session will start at 4, etc. There is only one exception for tomorrow, where it will start at 2:25. In addition to do this program, we paid attention to putting authors from different time zones on the time zones they are best. So for example, we put Asian presenters in the early sessions and US presenters later during the day. We also group papers based on topics. We really hope you will enjoy this program. Next slide, please. Then we will come to awards, but we have first advice to give. So we noticed that when people cite their data set and tools, they do it in 2 different ways. One way was to put a footnote with clearly identifiable tool set, tool chain. Another way is in the reference section. And there it's often gets lost with all the tools provided by other people or from the same authors in previous publications. So when you share tools and data sets, our recommendations is to try to make it more explicit what you're sharing in this submission. Next. So for the awards, we asked help from a selection committee composed of Anna Brunstrom and Mark Holman. So we tried to take people from the RTF who saw already a large number of papers and had the least conflict with the papers submitted to the conference. So now I'll hand over to Mark to present the awards.
Okay, can you hear me okay?
Yes.
Excellent. Okay, so actually I was, my wife and I were cleaning out a closet yesterday and I found this old PAM shirt here. You can't see this maybe. This is a PAM 2002 shirt. And I was asked why I still have it, so I had to wear it today. So Anna and I went through a bunch of the papers looking for choosing the awards. One thing that I will add to what Christelle said is that we found good quality papers that released data sets, but not a lot of them. So, you know, that's something I think that we as a community could work on is sort of releasing more data. That's not always easy, I know. But that's one note. So with that, let's go ahead and go to the next slide, which is the data set award, I think. Yeah, there we go. So this is a paper from CADA, UC San Diego, Northwestern, Old Dominican, Georgia Tech, lots of authors here. I'm not going to say everybody's name because I would probably butcher them. This is a paper on quantifying nations' exposure to traffic observation and selected tampering. So congratulations to these folks. This paper will be presented on Wednesday in the Security 2 session. It's the last session of the day. So it's a good paper and I encourage everybody to come and see the talk. I'm sure it'll be a good paper, a good talk. Sorry, it's early here where I am. All right, and then the next slide is the Best Paper Award. And this is Old But Gold Prospecting TCP to Engineer and Live Monitor DNS Anycast. It's another fairly large group of authors from USC, SIDN labs. And this paper will be given tomorrow in the second session of the day. There's a session on DNS and routing. And again, I got a nice chance to read this paper, and it's a good paper, and I expect a good talk from it. So please come and listen to that talk. And congratulations to all the authors of both papers. I think that's all I have.
Oliver, yeah. So we also have 2 keynotes during the conference. The first one will start right after this welcome session and will be by Johanna Amann that I will present right after. And the next one takes place tomorrow, and it will be, so the invited speaker is Les Deutsch from NASA, who will talk about deep space networks. So now my role is to welcome you to the session, the welcome session, and also to the program in all, and I will introduce the keynotes. But in the meantime, we really hope that you will enjoy these 3 days, and that you'll stay till the end to enjoy this terrific program, for which we had a lot of help from the TPC, from the organization people, and also from the awards committee. So let's move on to greeting Johanna. So Johanna Amann obtained her PhD at the Technical University in Munich in Germany, and she is now based in the US, where she works since 10 years for the International Computer Science Institute as a senior researcher. She's also a member of Corelight, a startup doing security, where she is a senior engineer and has an affiliation in the Lawrence Berkeley National Laboratory. She's a contributor to Zeek, which is the new name for a previously known software called Bro for deep packet inspections. And she's a part of the leadership of Zeek. She's doing research in network security and mostly doing passive monitoring. So today she will talk about passive network monitoring over the years. So my pleasure is to introduce Johanna, and I really hope you will enjoy her talk. I'm sure you'll enjoy her. So Johanna, the floor is yours.
Hi. Thank you very much for the introduction. Can you all hear me and see the slides?
Yes, we do.
Okay, that's great. So thank you very, very much for the introduction. So as you heard, I'm going to tell you the lessons from a decade of passive network monitoring. I was going to say a little bit about myself, but you mostly already heard that. So I have a bunch of hats. I am a senior researcher at ICSI in Berkeley. I work at a startup, and I'm affiliated with the cybersecurity team of the Lawrence Berkeley National Laboratory. So I was really excited when I was approached to give this keynote, because for me, I thought that this is a wonderful opportunity to hold a talk that also could have a different name. So basically, you can call this talk interesting network phenomena and problems you cannot typically write a paper about. Because if you do passive network measurements for a really long time, you encounter a ton of stuff that is interesting, or you encounter a ton of problems that you solve that are really interesting and novel, but they are not what's typically considered science. So you cannot really write a paper about them. You might be able to notice them in your paper, like in a few sentences or in a paragraph somewhere, or you might drop a few hints in a talk, but it's nothing that you really can write a whole paper about. And this gives me an opportunity to talk about this. So the main part of this talk will be about passive network measurements. So as you already heard, I started in ICSI a little bit more than 10 years ago now, so in 2011. And back then, one of the big things that the people at ICSI did was passive network measurements. So mostly look at internet traffic to determine things that go in the internet, which is really interesting because only looking at network traffic really gives you an idea or gives you the complete view of what's actually going on. It's something that you cannot really do any other way. And when I joined, one of the first things that we started doing is thinking about what is another interesting thing that we couldn't measure. And one of the things that we noticed is that there was one protocol that is really widely used, but had not really seen any big academic attention, which is transport layer security, or TLS. So the protocol which encrypts probably the majority of internet traffic nowadays, and might even be the most widely used protocol at the internet on the internet at the moment. So you might be thinking, well, I've seen a ton of paper and research about TLS, and there's a ton of statistics, but this was back in 2011. And in 2011, the internet was kind of a really different place from what it is nowadays. And I have selected a few headlines from things that happened on the internet in 2011, just to show you how different it was back then. So for example, 2011 was the year when Apple introduced iCloud. Google introduced Google Plus in 2011, which they then shut down again a few years afterwards. Microsoft acquired Skype, and Spotify announced that it is going to launch in the US. Now, if you search around, you can find a bunch of statistics nowadays about how much traffic is encrypted. I like this plot. This is from Google, where they show you how much of the traffic across Google is encrypted. And as you can see, nowadays, nearly all of the traffic is encrypted. When you go back to the beginning of the plot in 2014, it's 50%. And we had our discussion in 2011. So this was years before that. I was able to find a little bit of data that goes back further, which is from the Lawrence Berkeley National Laboratory, where I have data going back to the beginning of 2013. And this shows the amount of TLS encrypted connection versus the amount of HTTP connection. And you can see that in 2013, less than 30% of the connections were encrypted. This improved tremendously afterwards, but even nowadays, there is a solid 10% or so that are unencrypted. This is more than Google sees, but Google has a much more homogeneous environment where they control all of the servers, versus here, this is like user internet traffic and all kind of stuff that you see going over the network. So there's one more reason that we thought about selecting TLS. And this is that TLS, by definition, is a protocol where the payload, so the information that the users transmit, is encrypted. So this graph shows a TLS handshake with the green messages being clear text and the red messages being encrypted. And for us, this is actually really great because when we set up this research project, we decided really early on that we are not interested in what users are exchanging. So we don't want to see like users HTML pages that they access, or like the emails, but it's really interesting for us to know like the machine-to-machine interaction that decides which cryptographic parameters are used, which cipher suites that you use, and all that kind of information that really only mostly depends on the software that is used on both sides. And I think this comes into an interesting topic. Like when you decide to do a measurement like this, one of the first things that you should think about is the ethics of it, which is something that we did really early on. Because we decided really early on that we are really only interested in machine-to-machine communication. We don't want to be able to track individual users, which also means that we do not save the IP addresses of clients, which means that we cannot track what a specific person is doing. It's just like one random signal in a huge amount of connections that we see. And we, for example, also don't save client certificates that might contain user information. We save that there was a client certificate and how many certificates were sent in a connection, but we store no other information apart from that. So, and another thing that's really interesting that we wanted to do is, since this is a protocol where the payload is encrypted, we from the beginning thought that it would be interesting to have this as a distributed effort. So that it would be interesting to have several people that contribute data to us. And we thought that if we have an encrypted protocol, this might be much more possible than if we had some clear text protocol where we wanted to where you want to gather data, where you have to explain to people why this is okay. So let's say that you found some protocol that you are interested in and you want to perform a measurement, and it's actually you that wants to perform that measurement yourself. How would you go about doing a passive measurement? So you've probably seen slides like this before that show a typical network monitoring setup. So typically what you try to do is that you try to identify some kind of choke point. So typically you have something like your the network of your local chair, or the network of your local university, or perhaps even the network of your a small backbone network that connects a few university. And often these have a single border gateway that connects the local network to the greater internet. And that's a great point to get traffic at, because that border gateway will see like the complete traffic that passes from the local network out into the internet and back. And often you can instruct that gateway to just give you a copy of all that traffic by, for example, configuring a span port. And that traffic you then can send into a network monitoring system, like for example, Seek or Suricato or Snort, or whatever software you want to use to analyze your traffic. So when you do this in practice, one of the things that you probably are going to run into is the amount of traffic that is on the internet today. So this is the amount of traffic growth of ESNet, which is one of the research backbone networks in the US, which nowadays has about 100 petabytes of data exchanged per month, I think this is. And on this plot, it kind of looks like there was nearly no data till 2010. When you convert this into a log scale, it shows that this is nearly a logarithmic growth over time, which will continue going on. So what does this mean for you as a researcher in practice? It probably means that even if you're at a medium-sized university, you will probably have like several 10 gig or even several 40 gig or even 100 gigabit interface that you have to monitor. And how do you go from having to monitor this interface? So how does that work? Because you obviously cannot just point a 40 gig pipe at one process and expect it to analyze all of the traffic that you get. First, let me give you a slightly historical perspective of this. So this is a rack that was used to monitor network traffic. This is approximately the state of 2010 or so. On the left side, we have the rack, and on the right side, this shows what's actually going on here. So up here, we have a small fiber line that has the incoming traffic that is monitored. I think at this point of time, this is a single 10 gig line. And what we want to do is we want to distribute this one line of traffic across the machines that will do the analysis. Back then, individual machines were not super powerful, so we have two blade enclosures down here that have 14 computers each in it. So we want to distribute those 10 gigabit of traffic across 28 individual computers, so that each of the 28 computers only has to analyze like a few hundred megabits of traffic. How do you go about doing this? So in this case, the top device that the connection, that the traffic comes in, is what I call a MAC rewrite device. And it does something that's actually kind of clever in my opinion. So what this device does is it takes the 5 tuples of the connection. So you take the source address, source IP, destination IP, source and destination port, as well as the protocol, and hash that together in a way that both sides of the connection give you the same hash. And then you map that hash range basically to the 28 machines and give each of the 28 machines a part of that hash space. And what you do then is the clever trick. You take the Ethernet packets that come in and replace the destination MAC addresses with the interface MAC address of each of the computers, which means that now 1/28 of each traffic has the destination MAC of one of the blades down there. And then you just take the traffic and send it onto a normal 10 gig switch, which is not visible, it's at the back of the rack. And that switch then distributes the traffic across the 28 computers so that every computer gets its fair share of the traffic. What's also really neat, when you use the 5 tuple for hashing, this means that each computer gets complete like TCP and UDP sessions. So each computer sees the entire traffic that is exchanged for a specific connection and does not need to talk to another computer to get information about one specific connection. So nowadays computers are faster, and this is the same rack a couple of years later. As you can see, scientists have been building this because the cabling is a little bit of a mess. And now The situation is slightly different. We have 2 incoming links now, which are the 2 yellow cables up here on top, and we only have 1 machine down here that analyzes the traffic that is much more powerful. I think this one has like 70 or 80 CPUs. I don't exactly remember. So we have 2 incoming links now, because one of the link basically is the outgoing fiber from the network and carries all of the packets that go out in the internet. And one of the fibers is the incoming link. So it carries all of the traffic that comes in from the internet. This also means that the packets for like one TCP connection, for example, are distributed across 2 fibers, because you will see the incoming packets on one fiber and the outgoing packets on another. For us, it's still convenient to have all the packets that belong to one connection on one fiber. So the device on the top is what I call a flow reorder device. So this device takes 2 10 gig links and sends out 2 10 gig links again, but it makes sure that all of the packets that belong to a single TCP connection end up on a single link. And then we have our monitor machine, which in this case gets 2 10 gig links. The monitor machine does now internally kind of what we did in hardware before. So on the monitor machine, you get the incoming traffic to a network interface, and then you use some kind of system that distributes all of the traffic that you get on the network interface across virtual interfaces. One of the ways to do this is to use a Linux kernel feature that's called AF packet fanout, that basically does exactly what I said earlier. So it takes the 4 or 5 tuple and distributes the traffic so that every process gets full TCP, UDP, or whatever connections, and can see the full conversation. There's a bunch of systems that can do this. It's not just AF packet, there's also DPDK, AFXDP, NetMap, and a bunch of commercial vendors that all, in the end, from a usability perspective, work in the same way. So you get a slice of the traffic to your individual process. So after you have everything set up, so you have traffic that you have incoming and you distribute it across a number of virtual interfaces, you need something to analyze it. I typically use Seek, which, as was mentioned before, is a network monitoring system that has been developed at ICSI and at Corelight for a really long time nowadays. And you don't have to use this, and I'm not really going to deeply talk about it in the rest of the talk, but I have to mention a few basics. So basically, Seek is a scripting language for network traffic. And what happens is that Seek converts network traffic, takes network traffic and parses the protocols in it. And it then converts those protocols into policy neutral events that just tell you what has happened on the network. So you get events like there was a TCP connection that was started. There's an SSL connection that started. There was an SSL client hello. There were some certificates in an SSL connection. Here's a mail connection. A connection was torn down, and so on. And these events are then sent up into a script interpreter that runs some standard scripts that are shipped with Seek, plus user scripts that you can write. And those scripts then can write out log files or give notifications or take automatic actions. Or they also can create higher level events, feed them back into the event engine, and different scripts can handle those then. So now that we know how all of this works, my first plea is that, once you have, let's say that you have set up a measurement. So you have data, you have a protocol that you want to analyze, you have data that is flowing into your system, you have some script or some program that analyzes your traffic. The first thing that you should do really early on, even if it looks like the traffic, the data that you get is reasonable, check your data really thoroughly to be sure that your data is complete and internally consistent. It is often surprisingly tricky to do when you have a large amount of data and there are really mean things that can go wrong. And the first thing that I like to do is to check that your TCP and UDP sessions look reasonable. TCP especially is a great protocol because you get a lot of meta information, like you have a 3-way handshake, you have the nice teardown, and you have a bunch of information of stuff that goes on during the session. And Seek has one nice feature, which is for each for each connection in TCP or UDP that it sees going on, it writes out one line in a file that it calls the connection log. And one of the fields in the connection log, it calls the connection history. And that basically, that connection history has one letter for each thing that happened in the connection, like over time. In this case, you see that the first thing is there's a capital S. So capital letters represent that the originator of the connection, which is typically the client, sends something. In this case, the originator sent a SYN. Then here we have, in lowercase letters, the responders are typically the server sending back a SYN ACK. Then you have an ACK. Then you have both sides sending some data, and you have another ACK. And then you have the responder, so the server probably sending the first FIN for the connection ends. The client responds with OK FIN, and by the time that the server gets it, it probably already forgot about the connection again and just sends back a reset packet for good measure. But what you can tell when you see something like this in your connection log is that this was a full TCP connection. You had a normal setup, you have a normal teardown, and your one process saw both sides of the TCP connection and everything looked nice. If you have a ton of connections that look like this, like SADF, so all capital letters, this is really interesting because this means there obviously was a full connection, like the client was sent a SYN and then it was talking to someone, which means it must have gotten responses to its packets because it wouldn't just send an ACK without there being a SYN ACK first. And but you never saw the responses. And when something like this happens, this probably means that your traffic hashing is broken in some way, for example, and your processes don't get the full TCP connections, and you only see it like one side of the connections in a process. And the interesting thing is this doesn't actually have to be a black and white thing. So I recently set up a measurement where that took a while because it was hard to get data. And in the end, it looked like everything was running. And I was kind of happy. And I started doing this kind of analysis. And then what I noticed is that approximately 70% of TCP connections look completely normal. Like you saw full connections, everything matched. And for about 30% of connections, things were broken. And you only saw half of the connections and the other half was missing. This is obviously not what you expect because typically what happens is that either things work or either things are broken. It's not typically that some things work and other things are broken. This actually took me like a week or so of digging. And what was going on was that approximately 30% of the traffic that we were seeing at that time was wrapped in MPLS. And the system I was doing this was using AF packet, which is really widely used, which I pointed out earlier, to split up the traffic across processes. And it turns out that, at least in the kernel-based version that I was using back then, MPLS was not balanced by AF packet by looking at the 5 tuple anymore. Instead, it just stopped. And I think it balanced it by using the Ethernet addresses of the interfaces, which is for us the completely wrong thing to do because suddenly you don't have complete TCP sessions that go to individual processes. Another thing that can happen to you, which is really mean, is something like this. So you have traffic that is wrapped into some VLAN, which is really typical because VLANs are used everywhere. And this is okay, like everything can deal with VLANs. I think AF packet can deal with it fine, C can deal with it fine, you will get your data. But in more complex network setups, you can have the case where you have some connections that use different VLANs, and then you have some routers that use a more difficult route that also go over that link, which are not wrapped in one VLAN, but they have like 2 VLAN tags, or they might even have 5 VLAN tags on top of each other before you get to the connection data. And what's really interesting is that a lot of software stops analyzing the data after a couple of VLAN tags. I think, so you might have your seek running or whatever, and it happily unwrites the first 3 levels of VLANs, but then it sees that there's another one, and then it's just like, okay, that's enough, and just skips the data without ever telling you about it. And if something like this happens, you might be missing a significant amount of the data that goes over your link without ever noticing it. So basically, use additional tooling to make sure that the amount of traffic that you analyze actually manages the amount of traffic that should go across your link. All of the problems that I have told you about so far are things that happen inside your computer, but there's even more kind of mean to diagnose problems that happen in front of your computer. Like, let's go back to this which shows obviously the border gateway which sends traffic to your measurement machine. Let's say the border gateway for some reason is a little bit overburdened and drops 10 or 20% of the packets that are sent to your measurement machine in front of your measurement machine. How do you notice this? Because for a measurement machine, everything looks normal. You will still see like complete TCP sessions set up and tear down, probably because it's probably just data packets that are missing. Your interface statistics on the machine will be normal because it will be like, okay, I analyzed all of the packets that I got. There's one more way in which this can happen. This actually happened to me. We had a setup where we wanted to analyze an internet link, and we couldn't put the measurement machine right next to the router. However, we had plenty of capacity to just backhaul the data to the measurement machine over a different link. And the way that we did that is to tell the router to just wrap the packets into a tunneling protocol, in our case, GRE, and send it onto our measurement machine. And then this went on and sent it across a couple of switches and I think routers to our measurement machine. We started our measurement there, and on the first glance, everything looked kind of fine. But then we noticed that packets are missing. And what happened here is that when you wrap something in GRE, you obviously add a few bytes to the beginning of the packet, which means that maximum MTU packets are larger than the maximum MTU. Now, we thought about this before, and we thought that we had a jumbo safe path to our measurement machine, but it turned out that there was one router or switch that was not jumbo safe and just dropped packets. And yes, then you end up with that. So there's one fun way that Seek uses to determine when something like that happens. So Seek has a log file that is called capture loss.log. And basically what it does is it uses TCP gap AG analysis to determine the actual amount of data loss. And the way that this works is that when you have TCP, you can watch the AGs and the sequence number in the AGs to determine that there was data AG'd, but I never saw the data. But obviously the data must have crossed over the internet link that we have at some point of time. And if that happens, you can be pretty sure that the data actually went over that link and you just didn't see it. And you can use this to estimate the amount of data that was lost, even if that loss happens like far in front of your machine and far outside of your infrastructure. So you can see the actual amount of data that was lost, even if this is due to no fault of yours. So my plea again, check your data and your pipeline and do this repeatedly because things will fail after a while. And this might not even be your fault. Like there might be some new wrapping introduced, a new VLAN might be added. There might be more data and suddenly a router starts dropping packets. So it's really worthwhile to continue doing this. So the next thing that I wanted to talk about is I mentioned at the beginning that we wanted to not only do this ourselves, but we wanted external contributors for our measurements. How do you go about getting contributors to something like this? So it turns out that the answer is kind of obvious. You ask. It turns out that asking often gets you surprisingly far. And if you have like people that are network operators at universities or research networks, they often are actually interested in helping you and are interested in giving you data. However, I have to caveat this a little bit. It pays off to have good long-term relationships. Like we develop a network monitoring system and we have a reputation for doing this kind of stuff for a long, long time. And so we have established trust. Establishing trust with people takes a while, but it's really, really worth it because once you have done this, people are really happy to help you. And they also get something out of it. Like we point out weird things that we see going on in the data that we get, obviously, to the people that gives us data. Another nice thing that's really nice is when you do this, people that do this operationally already have monitoring hardware, etc. set up. So you get the data without having to spend your research money on it. But on the other hand, you don't control the data pipeline. So you cannot entirely guarantee its accuracy or bias in the end. Software updates are a little bit hard in this case because when this is used operationally, they run the software to get operational data. So when you want to update your measurement script, this will not happen immediately, and they might run some older version of the software, which means that you might not be able to get all of the new features that the newer version might be able to extract, which leads me to the next point. Think about your schemas early and make them extensible, because when you have external contributors, you will end up in situations where for years you will get different versions of the same data from different people, and you will have to process them simultaneously. And even if you think about it earlier, you probably will still end up with a bit of a mess because there will be something unforeseen in there. So the lesson so far, setting up passive measurements correctly takes quite a bit of time. You should really think about ethics early. This is really important, especially nowadays. Validate your measurement and continue to recheck them all the time. And debugging these issues can take really a surprising amount of time. And what's a little bit frustrating sometimes is that it's not always possible to fix issues that you find even when you identify the issues. And external contributors are great, but you don't control their pipeline. So the second thing that I wanted to talk about is more about our exact measurement that we have been doing, specifically about TLS and the protocol weirdnesses that we see. So the setup that we had is very similar to the pictures you saw before. We were interested in seeing the outgoing SSL and TLS sessions from our participants, which were bigger universities and research networks, to the internet. All of them were running Seek. We gave them a small script to collect some data, and they then uploaded the outgoing log files onto one of our machines, like typically each hour. And we would take those log files and put them into our database. All of this ran for nearly exactly 10 years. During those 10 years, we collected 236 million certificates from 443 billion connections. The plot on the right side shows the state of the CA ecosystem pretty much at the beginning of our measurement. Now, if you have read your TLS research, you might notice that 236 million certificates, that's not really that much, is it? And you're right, if you do an active measurement of the internet nowadays, you will get more than 236 million certificates. But these are the certificates that we actually saw being requested by users of the networks where we had access to the data, and there's a huge long tail of servers on the internet that no one ever talks to. And what's really even more interesting for us are the 443 billion connections, which means that we have access to a huge number of handshakes where we can determine what kind of negotiations did people do, what ciphers did they agree on, which protocol versions did they use in the end, which protocol versions did the client support, and so on. And this plot shows this shows the final negotiated TLS versions in the sessions that we observed since 2012. And what you might notice here is that at the beginning of our measurement, nearly all of the sessions were TLS version 1, some SSL 3 still, and some TLS 1.1 starting at the end of 2012. What's really interesting about this is when the different versions were standardized, because TLS 1.2 was standardized in 2008. So this was years before we even started our measurements. And we saw basically no traffic that used TLS 1.2. This also really shows how the importance of encryption on the internet has changed, because back then, like, it took years before deployment picked up. Like 50% of traffic only started to use TLS 1.2 sometime towards the end of 2014. So more than 5 years after the standardization finished. Versus with TLS 1.3, we saw preview versions being spoken over the internet even before the standardization finished. And after the standardization finished in 2018, you see TLS 1.3 taking up quite quickly to a significant percentage of the traffic. I also really like the next slide that I'm going to show you. So the traditional key exchange that is used in TLS is RSA key exchange. And with RSA key exchange, if you, for example, go and monitor the traffic, collect the entire traffic of a machine for a year, and after that year, you manage to somehow break into that machine and get access to the private key of the certificate. If you do that for the traditional TLS RSA key exchange, you can then decrypt all of the traffic that the machine sent during that entire year. Versus with perfectly forward secure ciphers, like DHE and ECDHE, the key that is used for encrypting the session is decoupled from the public-private key material of the certificate. So even if you manage to capture like a year of traffic and you manage to break into the server and get the key material from the server, this doesn't help you. You still will not be able to decrypt the data that you got. You might notice that this graph has a nice dotted line, and that after the dotted line, things start to change, like perfectly forward secure ciphers start to really pick up after this point of time. The dotted line shows the time at which the Snowden revelation happens. So we do not know that this caused this change. And this might have been something that would have happened even without it, but the timing is kind of suspicious. And this is something that obviously hit a lot of companies really hard. And it's probably also no accident that the traffic plots of Google, where they show how much of their traffic is encrypted, start a couple of months after these revelations and after they found out that internal traffic of theirs was being listened to. So now let me come to the actual thing that's like, what kind of weirdnesses do you see in TLS traffic? So first, let's talk a little bit about X509 certificates. So in TLS, X509 certificates are used to authenticate servers. And an X509 certificate, in essence, just is a AS1 data structure that has a bunch of fields. In this case, you have a version, a serial number, signature algorithm, issuer, not before and not after date, and the subject, which is, in this case, it's a certificate for google.com that's currently valid and valid for, I think, 2 months. Then you have the key information and a whole bunch of extensions that I'm not going to talk about. So this is a normal looking certificate. So during our measurement, one of the certificates that we came across is this one. And I'm going to give you a few seconds to look at this and try to see what's weird about it. So most of it is actually completely normal, but the interesting thing is this not after date. So this certificate was valid from the February 28th, 2016 to February 29th, 2026. The problem is 2026 is not a leap year. 2024 and 2028 are. So this date does not exist that the certificate is valid to. And it's really interesting when something like this happens, because one of the things that you should pay attention to when analyzing external data is try to figure out what your analysis software does with edge case scenarios like these, because you can encode this date in AS1. But what software does with it really varies. Like I think older versions of OpenSSL just gave you the string like that. So they tell you February 29th. Newer software of OpenSSL will just tell you this is an invalid date. Some software will stop parsing the certificate and be like, nope, cannot do this. And other software will be like, okay, this is March 1st, without any further comment and without telling you that there was anything weird going on in the certificate at all. We don't see this very often. So across our 10 years, we saw about 58 certificates with invalid data. Some certificates being, most of the certificates being more broken than this, and just containing like really, stuff like random 0 bytes in the data. What you also will see is you will see dates that might be widely outside of the date range that you expect. So we saw some certificate that said that it was valid at a specific date, at the date that the Bill of Rights in England was signed. So someone obviously did that on purpose and wanted to, did that on purpose, but this is outside of, for example, your typical Unix timestamp. So be careful what kind of data structures you use to save information like that. I also really like this certificate, which says that it is a version 4 X509 certificate. Now, the interesting thing is that there is no version 4 of X509. There's basically version 1 and 3, but you represent version 1 by a 0 in the version field and version 3 by a 2 in the version field. And I assume that these people hand rolled their certificate generation code and put in a 3 to express version 3 and didn't realize that they were doing it wrong. In this case, I think it's some cybersecurity company. This is not really rare. There's a bunch of people that we see doing this. We have approximately 20,000 certificates that do this for version 4, and I think we have a few handfuls of certificates doing it for version 2.2, and those probably should have been version 1 certificates because version 2 also doesn't really exist. But these are just the things that you can see going wrong in certificates. There are other things that you can see going wrong in, for example, the protocol. Like in TLS, the certificates are exchanged in a certificate message. And the certificates in the certificate message are supposed to be well ordered. So you're supposed to send the end host certificate first, followed by the intermediate certificate that signs the end host certificate, followed by potentially another intermediate leading up to the root CA that your browser knows. And this is not something that is like you should do it. The RFC is quite clear on this. You must do it like this, and each certificate must directly certify the certificate preceding it. So in practice, this is kind of hard or impossible because you don't actually know which root CAs the browser that you're talking to knows. So you might not be able to send the actual intermediate CA certificates required for this connection. But besides that, In practice on the internet, you obviously see all kinds of things. You see quite often that there is just the end host certificate and no intermediates. This is especially common on Microsoft servers, at least it used to be, because Windows has an alternative way to get the intermediate certificates if it doesn't know about them. It basically just looks at a URL in the certificate and downloads the certificate of some HTTP server. You might also find that there first is the end host certificate, and after that there is like an old certificate and a new one just was pasted in front of it, or that there is a self-signed test certificate, or that there are intermediate certificates that have nothing to do with the end host certificate, or that there's just trash data in there. What also happens sometimes, which I think is really fun, is that you can find data after the certificate. Like you first have the certificate and then there's more data afterwards. This is interesting because this kind of data is just ignored during parsing, because when you parse an ASN1 data structure, ASN1 has the length of all of the fields. And once you're done with all of the fields, typically your software just stops parsing and ignores anything that comes after that. And I have one more example that I wanted to show to highlight that it can really pay off to pay attention to what exactly is in the data that you get. So this is a certificate that we captured on Wire. And we noticed this while we were analyzing certificate transparency. So I'm not going to really talk about this, but certificate transparency is a system that Google introduced to make sure that the certificates that you get are trustworthy in the end. And you might notice that there's this weird extension down here that is CT pre-certificate SCTs that says random string goes here. So this certificate fell out of our analysis because it was like signature is not correct. And I loaded this into OpenSSL. And when I saw this, my first thought was like, well, I guess I have an old version of OpenSSL and someone didn't feel like implementing the output of the certificate. But it turned out that if you look at the actual ASN1 data structures, I was completely wrong. That field actually really just contains the string random string goes here. Like for comparison, this is how this is supposed to look like. You're supposed to have like this cryptographic data structure that has information about the log that signed the certificate and when it was added with a timestamp and so on, not just random string goes here. So what happened in this case is that someone apparently wanted to pretend that they are CloudFront, not to fool any users probably, but just to hide the traffic from network monitoring systems. So from people just like us. But the system that they used to create the fake certificates probably was not able to deal with the specific extension. And instead of dealing with it, they just put a random string in there and were like, oh, no one is going to look at that in any case. And then we come along and analyze this data really exactly and verify it. And they stand out like nothing, basically, which is really interesting because when you do something like that, you might actually make it so that your connections really become visible in comparison to other connections. We saw this actually being done a bunch. There was like 352 certificates for CloudFront that did this and 68 for Twitter. And I think it was some data centers in Africa that the traffic went to. And we were sadly never really able to pinpoint what the people that used this were doing. But I think we were able to find the actual certificate that they cloned. Like there were certificates that were exactly the same, besides the fact that the cryptographic key material was different because they used their own keys. And they were obviously not really signed. They just said we are signed by Amazon in this case, by Symantec in this case, but Symantec never signed those certificates. This is a small list of things we have seen. I mean, we also saw like completely invalid host names, like for example, UTF-8 host names in the list, and you're only supposed to have ASCII characters in certificates, invalid extensions. I mentioned extra and unordered certificate, missing certificates, data that is not certificate that is sent. You see, if you see passive network monitoring, you see a ton of auto-generated certificates. Like, for example, Tor uses certificates, and I think they rotate them every 5 minutes or so. When you do active measurements, you will not notice that much because you will get like a handful of Tor certificates. When you do passive measurements and you see someone connected to Tor and they rotate that certificate every 5 minutes, you will notice that there's something going on. You have certificates with really unusual choices in algorithms, like, for example, using like Russia-specific ciphers and fake certificates. So the main takeaways that I wanted you to take from this is When you start your measurements, or when you analyze your data, check how your measurement infrastructure deals with outliers and edge behaviors, because there will be something that you did not think of. And it is, if you see something weird, it's really worthwhile digging into it. And it's also really worthwhile to understand what your software does. Like, you do not want to have software that just ignores edge case behavior, or that just like, is like, nope, don't know that Cypher Suite, I'm going to not pass the certificate, because then you never will be able to figure these things out. The one thing that's a little bit about annoying when you do really deep digging is, assume you write a paper where you did a bunch of digging on all of the edge cases, you especially have like small spikes in your graphs and you have explained all of them and your paper is rejected. This can sting a lot, because when you resubmit your paper to a later conference, you probably will include more data, which probably will include different outliers that might even be bigger than the ones that you analyzed in the past, and you will get to do all of that manual effort again. Another thing that I wanted to mention is, so I talked about passive network monitoring all the time, but let's assume that you don't want to do passive network monitoring. Instead, you want to do active measurements. And I want to urge you, even when you are just doing active measurements, go and capture the traffic that goes over your measurement device, because this means you get repeatability, basically for free. Let's say you do a big measurement of the entire internet, and afterwards, really closely to your deadline, you are like, oh my God, I just noticed that in this case, I passed data incorrect. And this is something that happened on like 100,000 hosts, and I don't have the time to redo the measurement, or will be at a different time now. You might be able to go back to the data that you have in your traffic trace and just deal with the mistake that you made there, or look what exactly happened when you find something interesting there. And this works even for encrypted traffic, because you can save your key material. So you can just go and when you do encrypted, like HTTPS connections, for example, dump out the keys. Nearly everything supports that, so that you can go back and even look what happened inside the connections that you established. And just to point this out, this is not theoretical. This actually happened to us in a measurement where we noticed that I think we had a 7% bias or something like that. And back then we didn't capture the traffic of our active measurement. And so we were not able to go back to it, but we would have been able to completely eliminate the bias with it. And for some of our new measurements, we did this, and we published like PCAPs that they reach a pretty big size, but you can typically just, hopefully your university library or something like that will be able to host them for you. And this might even enable other researchers to do research with the data that you captured. So with this, I'm basically at the end. I wanted to highlight that this is not just work that I did. So this is work that I did with a bunch of people. So there were a bunch of papers written about this with a bunch of different people. And a lot of people contributed to this work. And this would not have been possible without them. I also wanted to thank the data providers. We had a lot of data providers that sent data to us for years and years and helped us when we had problems or had questions about their network infrastructure or had questions about something weird going on. And this actually takes quite a bit of time, and I'm really thankful for this. And with that, I'm at the end, and I would be very happy to answer any questions that you have.
Thank you, Johanna. So please either raise your hand or post your questions on the Slack. And then if you post on Slack, I'll relay your questions to Johanna, but feel free to raise your hand and voice your questions yourself. Really enjoyed in your presentation, Johanna, all the recommendations you're making for people wanting to do measurement research. I think many of your recommendations are useful also for other areas. So thanks for that. Oh, Mirja, you have a question? Okay, please go ahead, Mirja.
Yeah, hello everybody. Thanks a lot for the talk. Really helpful recommendations, as Crystal just said. I have to ask this one question. You rely a lot on TCP for your debugging part, right? And there's a new protocol coming up, which is Quick, which removes all this. So how much will this impact your work?
So if the majority of traffic switches to Quick, this will impact the work significantly, because this kind of analysis significantly, because from what I remember, Quick only contains a spin bit, and I'm not even sure if it made this into the final standard or if anyone will use it. So basically, you will not be able to see anymore, like if you're missing stuff. This is actually not just a problem for us. This is also a problem for like network operations, because you can use this like operationally to tell if your links in general are okay, or if you're using a significant amount of traffic. So yes, if like a majority of traffic switches to Quick, this makes this kind of analysis much harder. You are obviously still able to see if your local infrastructure loses packet, but you might not be able to see if there are any packets lost upstream. And you might have to go like much more manually to each device and look at the counters and so on. So you still can do it, but it would be much, much more work.
Yeah, so did you already start thinking about these problems, or is this something you delay to the future?
This is something to delay that we have not really thought about deeply, because at the moment there still is enough TCP. There hopefully will be for a while. And to a certain degree, there is not much you can do about it, because if the protocol gives you no information that you can use, there just is no data that you can use. And at some point, you just have to give up and be like, all of the traffic is Quick, encrypted. Well, guess we just have to hope that everything is okay, because you just cannot tell anything anymore.
Yeah, and then there are a few things that you can still recognize. You can still recognize the handshake to some extent. You can still recognize if data is flowing in both directions, and maybe you can do some packet size analysis. But it will be a completely different set of analysis you have to make. Yeah. So yeah, more work coming up for us all, I guess. Thank you.
Thank you.
Thank you. I have a question on how you deal with, so you see sometimes strange certificates. How do you deal with reporting them? And what are the reactions of the people you contact when you tell them something is not going the way it should be?
What kind of, it depends on the kind of strangenesses we observe. So partially this comes back to what I mentioned, that you should have relationships like with the operational people that run this optimally, so the people that provide you data. Because if you have a relationship with someone, they are typically really interested in helping you when you are like, hey, so we have seen this network, we get your network traffic, and there's this one thing that looks really weird to us. Do you have a thought? And they are often really interested in this and are either interested in dealing with it, if it's something that has to be dealt with, or interested in helping you figure out what the case for this is. If it's something weird that you see going on random traffic in the internet, this gets more difficult because, like, for example, like I said, we don't have the full information about the connections. Like, we don't have client IP addresses, and we also don't want to go out to random internet servers and be like, hey, so we see some connections that you do that are weird. Can you tell us what it is? So it really depends on how weird it is and who is involved. If we go and ask. One of the things that we did that I remember that was kind of fun is that really early on, when Google started the certificate transparency effort, we started seeing a few weird certificates that came from Google properties. And them, for example, we went to and we were just like, hey, so we noticed that you have this server and it sends a really weird certificate. Can you tell us what's up with that? In that case, they were experimenting with putting the cryptographic proofs that I showed in this picture, like this extension, not as an extension to a certificate, but have an extra certificate in the certificate chain that just contained this proof instead of a key. I think we are like the only people that have certificates like that because they never deployed that. They abolished that idea after a short test. But yeah, it really depends on who is involved. Sometimes we ask the people what's going on. Sometimes we ignore it. Sometimes we go to the network operators if it looks like something that they might be interested in and so on. So it depends on the individual case.
Thank you. So Kara, you want to go ahead and ask your question, please?
Sure. The data you presented was looking at the content of certificates. I'm wondering if you've seen weirdness in the timing or the volume or the response time of certificates as well.
What exactly do you mean by the response time of certificates?
So how long does a TLS handshake take, and does it ever take more than 5 seconds?
I have to admit that we did not really look at, I do not remember us ever looking into the exact timing of that, because we actually do not have that information. So you have to pick a little bit what kind of information you save, because you cannot just store everything. And we typically just have one timestamp for the entire connection, which is the first packet. So I'm sadly unaware. We had a small measurement that we did where we checked if there's any impact of using OCSP on the speed of connections, where we collected a little bit more information. There's a paper out of that for that. I don't remember the exact times. I think it was, everything was like in the millisecond area, but I don't. So typically the answer is, if you have seen something, typically I'm sure that there's some handshake that will take more than 5 seconds. Because, I mean, you probably know you can do weird things. So one thing that I remember, which comes back to make sure that you know what your software does, typically, like, your certificates are relatively small, and you see only they are all in one TLS record. But certificates can be up to 16 megabytes in length in theory. And sometimes you see these gigantic certificates that are split across records, and not all software can deal with that, and you might just lose that again. So, so I don't recall, but probably.
Thank you.
So there is a comment on Slack saying that encrypted traffic will be more and more important to consider in the future, comment from Mark, and that we probably need to involve the endpoints. Maybe one question that I have following up on this is, you have had people doing passive measurements for you. And maybe that's also why it's sometimes difficult to then go and say there is a problem, because you got the data from a third party. How easy is it to get people involved in your measurements, and how do you go about that? How do you go about motivating people to participate and participate in the long run?
So like I mentioned, I think a lot of this really depends on you having good relationships to people. Like in our case, we write a network monitoring system, people use it, and often people are actually really excited to finally be able to contribute something back to us and to help us in some way, which obviously is not really your typical case that you have. But even in cases where people didn't use the system before, if you ask really nicely and are able to point out why what you're doing is like important and interesting for the internet, you're able to get quite a bit of help. And communicating with people never has been a problem, because you typically have a long-term two-way communication channel with the people, where you can just hop on chat or something and talk to them about how things are going, and and like ask about weird things that you saw. And you're actually right. So we are thinking about this problem too. And like, there is a project that we actually have to add endpoint data to Seek, specifically to add information from the endpoint when everything's encrypted.
Anja?
So very nice talk. Nice to point out some of these complexities. Now, of course, a lot of measurements are done in places where you either don't see every single packet because you might only see one direction of the traffic, or you have to rely on sampled data. So how much of this kind of endpoint analysis can you still do? Where do things break? What are the big complications there?
So the answer is that we kind of cheat, because we actually have only done analysis in networks where we can see the entire traffic, because you are right. When you have, when you only have one-sided traffic, which happens more in big backbone networks, things get more complicated. So, sorry, let me expand on that a little bit. So some of the analysis that we do completely works on one-sided traffic. Seek traditionally has not been really super great, for example, at handling one-sided connections, but there are a few analyzers like the SSL analyzer, the TLS analyzer, that is perfectly capable of dealing with, I only see one side of the connection, will still dump out your log file, will zero out all of the columns that require both sides, but you will still get the data. But you are not able to obviously do things like determine how much packet loss there was, because I mean, there's a ton of packets lost. With sample data, I never had that, because we never were in a scenario where we only got sample data. Even when we get got data from like bigger network asymmetric routing, they were always able to just analyze all of the data that goes over a specific link. But things obviously get much more complicated then, because you will not be able to see a complete protocol handshake, and then you have to pick much more what you are analyzing. And I assume that typically you will just do much higher level analysis about the kind of like the split up of protocols that you see. You might still be able to see, do like analysis on TLS, but you will depend on the fact that you randomly get the handshake packets often enough to be able to say something about it. But yeah, it makes your work different, and obviously you have to be a little bit more careful about the conclusions that you can tell, because your data is not complete.
So this is a nice, brings me to another question is, when you rely on volunteers to do measurements, you may sometimes have some bias in your measurements. So it may be targeted more towards campus network than towards backbone networks, as you were saying, because the challenges are maybe even higher. So can you tell us a bit about this and how you can deal about bias in such measurements?
So this is a really great question, and something that I nearly wanted to talk about. And I actually have a great example in this plot here. So you might have noticed that there is this weird TLS13 goes down and TLS13 goes back up in this plot. And I actually looked at what happened here. And what happened is that, as I noticed, we have several contributors. And during this time, one of the networks that contributed data to us dropped out. And it turned out that the network that dropped out had a significantly higher amount of TLS13 traffic than the other network. And this is just something that happens. Like, networks are not the same. When you monitor at two different networks, you will never get the same data, because you have a different set of users that talk to different services. Like, if you capture data somewhere in China, things will talk to different services than when you capture a network somewhere in the US. So you will always be biased. In our papers, we always point out that the data that we have are from research networks that are mainly located in North America. And this is basically not something that, this is something you just have to accept. There is no unbiased set of data when you measure the internet. You just can report on what you see at your locations and be like, we think that this is something that will be similar in other locations that are similar to ours, but obviously there will be a difference if you have a different network. But apart from that, there is not super much you can do besides compare with different locations and see how they differ from yours.
Thanks. If there are other questions, please raise your hands quickly, because we'll soon release Johanna. So it is the last call for questions. In the meantime, thanks, Johanna, a lot for this great talk with lots of insights for the research community. I think lots of also insights for newcomers into measurements. So thanks a lot from all of us here.
Oh, thank you very much.
And if you have questions for Johanna, please go on Slack, and I'm sure Johanna will still be there for a bit.
Naturally.
So we will see you again in half an hour, so at 4 p.m. CEST for the rest of the conference. Thank you.
Thank you.